Ahora daremos inicio a la primera sesión de la preconferencia Productividad y Sustentabilidad y Políticas Públicas, Sinergias para mejorar el desarrollo agrícola. Esta sesión se centrará en la evolución histórica de la productividad, una comparación entre países y los vínculos entre la productividad y los recursos naturales. Iniciará la exposición el doctor Christopher O'Donnell. El doctor O'Donnell es profesor de la Universidad de Queensland, es coeditor del Journal of Productivity Analysis y miembro distinguido de la Australian Agricultural and Resource Economic Society. Sus intereses de investigación se centran en programación matemática y métodos estadísticos para medir y analizar la productividad y el cambio de eficiencia. Ha sido consultor para organismos como el Banco Mundial y la Organización para la Productividad Asiática, entre otros. El doctor O'Donnell nos presentará un panorama histórico del análisis de la productividad. Con ustedes, el doctor O'Donnell.
Lo siento, no español. Thank you very much for inviting me to come. Thank you to ODEPA, University of Talca, and the USDA for running this pre-conference and conference, and thank you very much for inviting me to come here. Productivity analysis is something that many people are interested in, often because they all think of productivity slightly differently, and to get an understanding of why it is that different people think of productivity differently, it's useful, I think, to take an historical perspective. And so what I'm going to do today is I'm going to go back in time a little bit to the middle of last century and talk a little bit about how people viewed productivity then and how productivity has evolved over the 70s, 80s and 90s to today, so that we can get a better understanding of how people measure and explain changes in productivity. So historically, productivity has been defined as a measure of output per unit of input. These definitions go back to the 1930s really, but the work by Dale Jorgensen and Zvi Grigers in the 1960s was very much focused on this idea. However, in more recent times, when we see work on productivity, we see productivity sometimes defined as a measure of technical change. Sometimes it's defined as a measure of technical change and efficiency change combined. Sometimes, most recently in fact, it's defined as a residual. So we have many different definitions. What I hope to do today is explain to you that under certain conditions, all of these definitions are perfectly valid under certain assumptions. Productivity analysis to me involves several things. It involves first and foremost defining what we mean by productivity, and I'm going to talk about that. Then it also involves measuring productivity, and historically it's been common to measure productivity using well-known quantity indices, Fisher, Tornquist and so on. These indices have their shortcomings. In particular, they don't satisfy some very common notions that we get from measure theory, and I'm going to explain to you some of those details. However, it is possible to measure changes in outputs and inputs, and therefore productivity, using indices that have got nice properties. I'm going to talk a little bit about what I mean by the term proper indices in that context. The other element to me that is important in productivity analysis is it's not just defining and measuring productivity or productivity change, it's explaining changes in productivity. And if we think of productivity as a measure of output per unit of input, then as an economist, I see many different economic models for explaining how outputs and inputs are determined. So if I want to explain changes in an output-input ratio, there are many models that help me explain changes in outputs and inputs and therefore productivity. So a lot of my work is in the area of stochastic frontier analysis. It's just a technique, one of several, that can be used to explain variations in outputs and inputs and productivity. And some of the most general stochastic frontier type models are models that allow you to explain productivity change in terms of technical change or technical progress, changes in the environment, changes in technical efficiency, which is the efficiency with which technologies are used, changes in returns to scale, economies of scale, economies of substitution, concepts that economists are familiar with. So I'm going to be running through these details. So there's essentially 5 parts to my talk. I'm going to start by talking about productivity as an output-input ratio. This is a concept that comes from the 1950s or earlier. And I'm going to talk about productivity as technical change. Some people define productivity as a combination of technical change and efficiency change. Most recently, a lot of people, particularly in the macroeconomics literature, define productivity as a residual. So I'm going to explain where these concepts come from and how people measure productivity in this context. And I'm also going to talk a little bit about where that leads us. It leads us to productivity analysis today. So this idea that, I've got a number of quotes here from lots of different famous people over the years. The idea that productivity is a measure of output per unit of input goes all the way back to the 1930s. In the 1960s, there was a lot of work done by the NBER and by Zvi Griliches and Dale Jorgensen on productivity. It was recognised that productivity was important. As Kendrick writes, you know, the story of productivity, the ratio of output to input is at the heart of the record of man's efforts to raise himself from poverty. There's a whole lot of other quotes here. But they're all saying the same thing. They're all saying that productivity is a measure of output per unit of input in some way. And, you know, here's more. I mean, we could go on for pages here. People have been talking about output per unit of input for a very long time. And as Hilton says here in this second quote, it's not a terribly deeply theoretical concept. It's a simple idea, output per unit of input. Other people are saying there's no disagreement on this general notion. Well, there is actually, but there wasn't at the time. Okay, so output per unit of input, and that's the starting point for me in my work as well. Productivity is a measure of output per unit of input. Now, this is a fairly simple thing when you've only got one output and one input. When you've got more than one output and more than one input, then you run into an index number problem. You have to measure changes in several outputs, and you have to measure changes in several inputs and then get a measure of output per unit of input. This is the basic idea. In this figure, on this vertical axis here, I have basically a measure of total output. On the horizontal axis, I have a measure of total input. And I have 2 points here. Point A with this much input and this much output. Point B, this much input, this much output. If productivity is an output-input ratio, then it is the ratio of this amount of output to this amount of input. It's just the slope of this dotted line. So when you look at these diagrams that I'm going to show you today, productivity, just view it as the slope of these dashed rays. And you can see here that the productivity at point A is lower than the productivity at point E, and what we're interested in measuring that change, and we're interested in explaining that change. So how do we measure productivity? Well, it's most common to measure productivity by dividing an output quantity index by an input quantity index, and the most common indices that are used for that purpose are Fisher, Tornquist and Malmquist indices. Now these are indices that were developed in, well, talked about a lot, I should say, in the 1920s. Irving Fisher's book, The Making of Index Numbers, discusses a lot of the properties of these sorts of indices. And all of that discussion was in the basis of binary comparisons, which means comparing only two observations. And consequently, these indices don't satisfy a transitivity axiom. Transitivity axiom is a property that allows you to make comparisons involving more than two observations. And so, generally speaking, they shouldn't be used to make multi-period, intertemporal, or interspatial comparisons. And to give you an example of why that is so, I'm going to show you some toy data. This is just some artificial data. And just explaining this table, I'm going to add columns to this table as I go. But this is just a table with data on a single output queue and three inputs, X1, X2 and X3. If you like, you can think of them as capital, labour, materials, whatever you like. As we go down these different rows, we see observations on, you can think of them as firms, or you can think of them as the same firm in different time periods, using different inputs to produce different amounts of outputs. And so this column here is, these are Fisher index numbers. And what you can see is that some of these numbers, without knowing anything about index number theory, common sense will tell you that some of these numbers are sensible. So, for example, these indices are all comparing the input-output combinations of different individuals with the outputs and inputs of firm 1. And this productivity index, right, 1.786, is saying that firm B, if you like, is 78.6 times more productive than firm A, and that's because it's using 42% fewer inputs to produce the same output. This one here, 2.37 times more productive because it is producing 2.37 times more output using the same inputs, and so on and so on. 3.15, that makes perfect sense. If you divide 2 by 0.919, you get 2.176. This is just simple mathematics, okay? This is just simple principles of measurement that would give us these numbers. But in this table, there's a couple of numbers, I've got them highlighted in red, that don't make a lot of sense, in the sense that if you have a look at this firm D, if you like, and you look at firm E, they're both doing the same thing. Same input, same output, and yet the Fisher index is assigning them different numbers. This is not consistent with measure theory. The measure theory says that we're in the business of assigning numbers to objects or bundles, and measure theory says that the patterns that we see in the bundles should be reflected in the numbers we assign. So if you have two bundles that are identical, measure theory says you should assign them the same number. And here the Fisher index is assigning these two bundles different numbers. That's a problem. It derives from this transitivity property. I'm not going to go into the details. This number down here is also a problem. What you'll notice is that this firm down here is using twice as much of every input as firm E. Firm E is using 1.05, 0.7, 0.6. This guy's using twice as much of every input. So, you would think that this firm would be half as productive as firm E. You would want this number to be half as big as that, and it's not. Right? So this again is violating common sense and basic principles from measure theory. Now that's not surprising really, because the Fisher index wasn't designed for making multiple comparisons. was designed for making just comparisons involving two observations, which means we can compare D with A and that's it. The same with the Tornquist index. You get the same sort of, these red numbers, you get the same sort of inconsistency. So we shouldn't be using Fisher and Tornquist indices to make intertemporal or interspatial comparisons. People realised this in the 1960s. They realised that this transitivity thing was an issue. They said, well, how are we going to make comparisons over multiple time periods? Now, the OECD is quite specific about how to make intertemporal comparisons. In the OECD Productivity Manual from 2001, they claim that economists are quite unanimous that you should make intertemporal comparisons by chaining Fisher and Tornquist and other indices. It doesn't work so well. These two columns here are chained Fisher and chained Tornquist indices, and all of these numbers are fine, right? We've got the 1.786, the 0.237, and these two numbers are equal to each other, which is sensible, right? But we start moving down the table, and all of a sudden, firm V, which is producing 3.15 times more than firm A, is regarded as 3.68 times more productive, right? And the chain Tornquist index even worse. All of these numbers in red, they don't make any sense, right? These are not consistent with basic notions from measure theory. So that's a problem with chaining. What about if you want to make comparisons across space? Well, the received wisdom is that you should use multilateral indices. Caves, Christensen and Dewart in 1982 proposed taking basically the geometric average of many different binary Tornquist indices. This idea actually extends back a little bit earlier to the 1960s. Altito, Coase and Zulk all simultaneously developed a method for geometric averaging of Fisher indices, and that index is called an EKS index. The EKS and the CCD indices are very, very widely used to measure productivity across space, but we're going from the frying pan to the fire. There's very few numbers in these columns that make any sense, and this is because these indices don't satisfy some other very basic properties of index numbers like proportionality, which say, for example, if you've got twice as much as me, the index number should take the value too. EKS and CCD indices don't satisfy those properties. So how do you measure quantity change properly? Well, there are many what are called proper index numbers, and proper index numbers are constructed by essentially just taking an aggregate of aggregating one output vector into a scalar measure, aggregating a different vector into a scalar measure, and then just taking the ratio of those two. The key is how do you do the aggregation? And this formula here is saying simply do the aggregation by using a function with some very basic properties, non-negative, non-decreasing, linearly homogeneous. If you aggregate outputs that way and you take the ratio, then you're going to end up with an index number that's got lots of nice properties. You can do that on the output side, you can do it on the input side, and a proper TFP index is just the ratio of the two. And there's many of these, there's thousands of them actually, there's thousands of these indices, but the ones that appear in the literature are an index called the low index, a geometric Young index, and one that doesn't appear in the literature yet, but it will early next year, is a benefit of the doubt index, right? And if we apply those indices to this same data, then you don't see any red, because you see what common sense would tell you to be sensible measures of productivity across the board. These are indices that satisfy common notions from measure theory. All right, so that's the measurement story. Which one do you choose? Which of these proper indices do you choose? You choose any one you like. It's a matter of taste. And this idea of choosing indices according to your taste goes all the way back to Samuelson. I like Samuelson. Samuelson, who was the first American Nobel Prize winner in economics, had quite a lot of interesting things to say about index numbers, and this was one of them. There is no perfect index number formula, but what you can do is you can choose an index number formula that is proper, and that's always a very good start. Now, many people view productivity as technical change. Where does this idea come from? Well, it comes mainly from work of Solow in the 1950s, and so he used the phrase technical change to mean basically any kind of shift in the production function. And Jorgensen and Grillikers, they identified that with productivity. Dewert and Morrison, they talk about productivity growth and technical change synonymously. They don't make a distinction between the two. Other people, even more recently, they simply equate TFP with technical change. And where does that idea come from? Well, this is the same diagram I gave you before, right? Points A and E are in the same places they were before, but all I've done here is I've drawn in some production frontiers. Okay, so this is a production frontier, this straight line. It gives the maximum output that's possible using a given set of inputs in a given period, and it's a straight line indicating that you have constant returns to scale. And the formula for it is simply some function of x, right? Non-negative, non-decreasing, linearly homogeneous function of inputs, multiplied by some factor that varies over time. And in period t, this is where it is. In period s, that's where it is. And the difference, well, that's technical change. That's what the t represents. So, yes, the difference between those dashed lines I saw you before can be viewed as a difference in a change in technology or technical change. So this idea of technical change being the driver of productivity goes all the way back to papers like Solow. So Solow had an equation. I don't want to get too technical, but he had an equation in his model that says that total output or aggregate output is a function of inputs and time. And this function here is non-negative and non-decreasing and linearly homogeneous. And so, simple accounting rearrangement. AT can be written as the aggregate output divided by this non-negative, non-decreasing linear function, non-homogeneous function of inputs, which is a valid way of aggregating inputs. And so AT here can be viewed as a proper measure of productivity. So, in this formulation here, this represents technical change, but because of the properties of this production function, it can be viewed as a proper measure of TFP as well. How do you estimate it? There's a number of different ways of doing it. Solow did it one way, bad way. But an easier way to do it is just using least squares regression or something. So commonly what happens is that people assume a Cobb-Douglas function or something like this, and they write out a regression model. And in this particular case, if you assume that this function is a Cobb-Douglas function, this is what the relationship between inputs and outputs looks like. And this AT term here, this AT term is in fact the anti-logarithm of the residual. Alright, so what that means is that you can estimate this equation by some kind of, econometric estimate of least squares or something. And if you take the anti-logarithm of the residuals, you have a proper measure of productivity. Right, so this is the origins of this idea that productivity is a residual. Changes in productivity are a residual. And so if you apply this to the data, I did mention that Solow used a method for calculating AT that had a few issues. If you follow that method, you get quite a few numbers in red. But if you just do simple basic least squares regression and take the anti-logarithm of the residual, you get numbers that make perfect sense. This number is equal to 1, this number is 1.786, 2.37, these two numbers are equal to each other, this number is sensible, 3.15, sensible, and this number here is half as big as that one, right? That's the sort of pattern that we're looking for in a sensible index number. Subsequently, people said, oh no, productivity is more than that. Productivity is more than technical change. Not everybody operates on the frontier. Those points aren't always on the production frontier. And Prescott, in fact, said so Prescott's another Nobel Prize winner, and in his Lawrence Klein address in 1997, published in the International Economic Review in 1998, he said we need to explain productivity in terms of more than just technical change. Well, in fact, people have been doing that for a few years prior to that. Rolf Fair et al. In their American Economic Review paper, they defined productivity growth as the product of not just technical change and efficiency change. Right? And this is a very famous paper. And basically we've still got points A and E here, but instead of the period T frontier running through point A, I've drawn it here. And so point A here is below that frontier, and this shortfall in output that is possible using a given set of inputs, this shortfall in output is a measure of technical inefficiency. So the difference here is due to two components, technical change and technical efficiency change. Okay, so that's a little bit more, we're starting to get to a stage where we're trying to explain changes in productivity actually. How did they estimate this thing? Well, this is actually what a Malmquist index does. A Malmquist index actually measures that difference. And problem with Malmquist indices is it's another one of these binary indices like Fisher and Tornquist. Okay? Now I won't go into the details of how they estimate it, I'll just show you what the results are. So there are in fact many more observations in the data set than I showed you on those previous slides, and I've just picked a few different ones. I've picked these different ones because these all happen to be observations on a single firm over many time periods, and that's the context in which this index is used. But you can see here that this number here, 2.539, is saying that a firm that produces 3.11 times as much output using exactly the same inputs is saying it's only 2.539 times as productive. Okay, that's a problem, right? That doesn't make sense. And similarly down here, and the fact that these two numbers are different, that's another problem. I mean, there's problems everywhere. But the good news is, you can break it out into two components, technical change and technical efficiency change. What about a residual? Well, this paper by Ollie and Pakes, talk about productivity. They actually define it as a residual. Right, now this paper's been cited more than 4,700 times. This is the way many people today view productivity as a residual. And it's a residual from anything. If an industry is a single product and it's a production function residual. Otherwise, it's a residual from a reduced form sales equation and so on. So basically today, many people just view any kind of a residual in any kind of an econometric model as a measure of productivity. Sometimes it is. We saw that in the case of the Solo model, under those restricted assumptions, constant returns to scale and so on, the residual is a proper measure of TFP. But generally speaking, it's not. So we're back to a stage where the explanation for the change in productivity is a residual. Now, in an econometric model, a residual is a measure of statistical noise. It picks up a number of things, functional form errors, measurement errors, emitted variable errors, and so on. So that's basically what's going on here. The difference in productivity is basically statistical noise. Now, does it matter in practice? Sometimes it does. So I won't go into the details here, but Ollie and Pakes, they specify again, output is a function of this function of A and F, and some stuff at the end. Those people who are familiar with this literature will recognise this equation. In this equation, this omega here represents productivity, and eta represents either measurement error or a shock to productivity. And subsequently, you estimate this thing, and an estimate of this bit at the end is used by Ollie and Pakes as a measure of productivity. You can't generally do that unless you've got some very special conditions. I'm not going to go into the details of how it's estimated, but it's pretty fancy. It's a simultaneous equation system, and it's actually very difficult to estimate. The good news is, for people who don't really want to go into the details, is that you can push the button and state it. and you can get the numbers out. And that's what 4,685 people, I think, have done, right, with the 4,700 people who have cited it. And I'm one of them. I did it too. The code in Staden, there's actually a couple of codes in Staden that you can use. Levinson and Petrin, they actually did a very similar thing. It's a generalisation of this model, and more recently, Wooldridge has also estimated productivity in this framework. Only comment that I would make is that if the assumptions underpinning these models aren't true, then you're going to end up with biased predictors and estimators of efficiency. What sort of assumptions are there? Well, I don't know. Prices are firm invariants, or all firms face the same prices, that irrespective of how much labour is used, a constant proportion of the capital stock is going to be used in each period, that firms know how efficient they're going to be in the coming period but don't know how efficient they're going to be after that, da-da-da-da-da-da-da-da. Well, to me, I guess the proof is in the pudding. Here's the pudding. These are the Ollie Pakes measures of productivity change, Levinson, Petrin, Wooldridge. There's red numbers everywhere. So all this indicates is that the assumptions underpinning those models, they might be valid, but they're not sufficiently restrictive to enable you to interpret the residual as a proper measure of productivity change. So what do we do today? Well, these days, productivity is still regarded by many as a measure of output change divided by a measure of input change. And I have a couple of papers where I have taken these proper productivity indices, the low index in one paper, the geometric Young index in another. I've used DEA methods in one of these papers to decompose a low index into measure of technical change. I put it in inverted commas because even back then, I didn't appreciate the difference between environmental variables and technology. A measure of scale mix efficiency change, that's economies of scale and economies of substitution, and a measure of technical efficiency change, and we know what that is. In a more recent paper, I looked at a different productivity index, again a proper productivity index, and that breaks out that index into all of those components. But because it's a stochastic frontier model that includes a measure of noise, there's a noise component in that decomposition as well. So this is basically the idea. Points A and E and C are in the same places that were before, but I haven't got straight lines anymore because I'm allowing for variable returns to scale. I also actually have a couple of different functions here. That's because I'm also allowing for differences in output and input mix, and to represent that in 2 dimensions, you actually need 2 different frontiers. The distance from A to C is still a measure of technical efficiency. The distance from E to C to E is a measure of scale and mix efficiency. There would be another E in another period, in another environment, and if we do that, then we end up with components that represent environmental change and technical change. Oh, details. Here are the numbers. Okay, so the numbers, these are the low TFP numbers that I showed you before, and using data and development analysis, many people like to use that. You can break that out into components that represent differences in scale, mix and technical efficiency. If you work with a stochastic frontier model, this is what a stochastic frontier model looks like, and I guess this is a generalisation of the Solo model. Solo had AT here, and he had f of x. Well, I've got environmental variables in here, I've got an efficiency measure, and I've got a noise component. As it happens, Solo assumed there was no noise, so he assumed that bit away. As it happens, he assumed there was no technical inefficiency, so he assumed that away. He assumed there was only one output, so that little bloke disappears. He assumed there was no environmental variable, so that disappears. And so if you make all of those assumptions, you're back to the model of Solo, and technical change is a measure of productivity change. Won't go into the details again. These are the numbers. So total factor productivity, these are the numbers that I've been showing you. These numbers are the ones that are proper index, and you can break that out into a technical change component, an environmental change component, This component scale mix measures economies of substitution in scale. This is a technical efficiency change component. This is the change in statistical noise. And I guess what that's telling us at the end here is that there isn't any. Okay, so for this particular toy data set, and I have to say, I didn't make up this data set with a view to having no statistical noise. I just made up the numbers, and then I just kind of ran the model, and I was pleasantly surprised to see that, well, you know, just a very simple model explains everything very well. So that's basically it. That's the story. As I say, historically, and even today, productivity is conceived of as an output-input ratio. And the problem, a problem I think, with modern productivity analysis is the way outputs and inputs are measured. They're typically measured using indices that don't satisfy basic axioms from measure theory or index number theory. And so what do those numbers tell us? So when I look at numbers like this, I don't know what these numbers mean. This number here, 0.380. So we've got a firm that's producing the same outputs using 42% less inputs. It should be more productive, and this is saying that it's actually 62% less productive. What does that mean? I don't know what that means. I don't know what any of these numbers in red mean. And so my point is that analysis of those index numbers isn't going to tell us a lot about productivity, or for that matter, anything else that an economist might be interested in, because they're not measuring changes in quantities, but they're not measuring changes in prices either, nor are they measuring changes in revenues or costs or profits. So I don't know what they're measuring. Second step, I think, in doing productivity analysis is once you've measured things properly, then you can start talking about explaining them. And as an economist, it seems to me that, you know, we have, as economists, we've got thousands of models that tell them how inputs and outputs are chosen. Oh, they're chosen to maximise profits, or they're chosen to maximise profits in the face of uncertainty about this, that or the other. So we've got models that tell us that the Q's and the X's are functions of prices and this and that and the other. Well, if you want to explain changes in an output-input ratio, you can use economics to explain changes in the outputs and the inputs. And so you can use established models of firm behaviour to help explain how outputs and inputs and therefore productivity is determined, and that's the way, some people are starting to do it now. And that's where I'll leave it. Thank you very much.